And walking through this problem does not matter if we're talking about a minimization problem or a maximization problem. The process is the same. They're all optimization problems, whether you're finding the minimum or the maximum. Here we have a rancher planning to make 4 identical adjacent rectangular pens against a barn, each with an area of 400 square meters. What are the dimensions of each pen that minimize the amount of fence that must be used? Okay, so the thing that we're going to try and optimize, in this case we're minimizing, the thing that we're trying to optimize is the dimensions of the pen. Okay, in other words, how big are these sides? All right. And let's look at what the total amount of fence being used is. We've got this, 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 this that are all the same. We can call those widths. So 5 widths, and then we can call this long one here a length. And that would be the perimeter, if you want to call it that, of fence being used for these pens, because this side doesn't need any sitting up against the barn. All right, so this is the thing that we're going to try and optimize. In other words, we're going to be taking the derivative of this function, but we really need to make sure that we have it all in one independent variable. So let's see, what else do we know? We know each of these is 400 square meters. So in other words, this width times this length, the width times the length, is equal to 1,600 square meters altogether. Okay, so we can use this function here, solve it, get one variable for the other equation. So let's go ahead and figure what L is in terms of W. It's going to be 1,600 divided by W. So here I have 5W plus L is 1,600 over W equals P. So all I've done here is to get the equation where we have just one independent variable. Now my job is going to be go ahead and take the derivative, because remember, we're talking about functions increasing and decreasing, or decreasing and then increasing, and that's where the extrema happen, and that's where we have optimization occurring. So we're ready to take this. We've got dp dw. The derivative of the perimeter with respect to the width is going to be equal to 5 minus 1,600 over W squared, just by simple derivative rules there. Okay, so we've got dp dw is equal to 5 minus 1,600 over W squared. And we're figuring this is going to be something that minimizes. In other words, we've got behavior of this function that moves down and then moves up. So where does this minimum occur? It's going to occur where, well, we've got here the derivatives, the slope of those little tangent lines are negative until they get to here, then it's 0, and then they become positive slopes. So it's wherever the derivative, this thing that we just found, it's wherever the derivative has a slope, right? The slope is equal to 0. So I'm going to say 0 equals 5 minus 1600 over w squared. And then our job is to go ahead and solve that. So 1600 over w squared equals 5. I'm going to take 1600 and divide by 5 is going to be 320. And then if I take the square root of that, then w is going to be 8 square roots of 5. We don't care about the negative. We can have a negative width there. So width is going to be 8 square roots of 5. And I know that my length was 1600 over the width. So L is 1600 over 8 square roots of 5. I get 200, and I'm going to put square roots of 5 over 5, rationalizing that. And so that's going to give me 40 square roots of 5. So the dimensions of each pen, the width is going to be 8 square roots of 5 meters is that measurement. Okay, and the length of each pen is going to be that 40 square roots of 5 divided by 4. We have 4 of those, so it'd be 10 square roots of 5 meters.